Good evening, all. I welcome you all for the last day of our online 1 week faculty development program on electric vehicle drive systems. Today's session is going to held by Dr. S. Saravanan. The session is about the challenges in electric motor design for electric vehicle. I introduce her to the participants. Dr. S. Saravanan is an assistant professor in the Department of Electrical and Electronics Engineering at the SRM Institute of Science and Technology. He has completed his bachelor degree in Electrical and Electronics Engineering at the VLB Janaki Ammal College of Engineering and Technology. He has completed his masters in Power Electronics and Drives at JPR Engineering Colleges, Anna University. He has completed his doctoral program in Anna University, Chennai for the topic Design and Performance Analysis on doubly salient outer rotor SRM using different materials and pole configuration for EV application. Sal is having more than 10 years of teaching experience, and he has published more than 10 international journals, and he has presented more than 10 papers in various conferences. He is an active researcher and an active speaker. I welcome you, sir.
Thank
I
you
hand
for
over the
the nice
session to
introduction, sir.
Dr. Saravanan, sir.
Yeah, sure,
Thank
sir.
you, sir.
Good evening, one and all present here. Can you hear my voice?
Yes, sir. It's audible.
Yeah. I'll present my screen.
Yes, sir.
I think my
Yes, sir.
screen is
Yes.
visible now. Okay, I will start this
Sure.
session. I am Dr. S. Saravanan from SRM Institute of Science and Technology in Faculty of Engineering and Technology. I am working as assistant professor in Department of Electrical and Electronics Engineering. Today, our topic is challenges in electric motors design for electric vehicles. In this session, we will discuss how the motor design is more important for any electric vehicles and what are the challenges the researchers facing in day-to-day research. So this is the objective of our talk today. Okay. Yes, the motivation why we are designing electric motor for any application. There are many applications we have for electric motor. In those, I have listed some of the applications. In home applications, most of the home applications are using electric vehicles. In transportation system, like what we are seeing today for the electric vehicles. Then manufacturing and industrial areas for conveyor belts, and in every application they need electric motors. In robotics, for robotic arms, they need electric vehicles, especially they apply special electrical machines for robotics. Then in medical field, aerospace and defense also, these are the major areas they use special electrical motors for the application. Okay, so that is why we need to construct a motor in an efficient manner. Okay, so these are some of the applications the electric motors are used. Okay, especially special electrical motors are used. The EV generation growth. Here you can see the first EVs developed in the year 1832. So in 1832 itself, the first electric vehicle was developed. Then in 1891, Thomson have started to develop EV batteries, especially the batteries for electric vehicles. Then Porsche come into market to produce the first ever electric car. They have started to produce electric car in the year 1899. Okay, then first hybrid motor have been developed in the year 1920. So in 1920 itself, a hybrid electric car have been started to develop. Then in 1960, after 40 years, the EV start develop again. Okay, there is a gap between 1920 to 1960. There was a big gap. After that, they started to build again for the electric vehicles. Then Toyota Prius started to produce in mass level the hybrid electric cars in the from the year 1977. So from 1997, they started to produce the hybrid cars in a massive way. Okay, so in 2008, the Tesla launches the first ever their electric car. Then uh, till date, we know the Tesla is the major electric vehicle producer all over the world. Then in 2017, the many automobile industries are developed in the EV market. Okay, in 2019, the Tesla have uh, marked a target of selling 1 million cars. Okay, in 2021, the EVs are the only future in automobile sector. They started to believe. Okay, from the year to 2021. So these are the EV generation from the year 1832 till 2023. Okay. Then I have listed and mentioned some of the electric motors which are used in our real-time EV manufacturers. Okay, so the first one in Tesla, they usually use induction machines. In Toyota Prius, this one is the permanent magnet synchronous motor, which is used in Toyota Prius. And in 2004 itself, they started to introduce permanent magnet synchronous motor in their EV. In 2010, they have modified their model. This one is the permanent magnet synchronous motor again. In Hyundai Sonata, this is the motor they are using in from the year 2011. In Nissan Leaf, from 2012, they started use this machine. Then Honda Accord, this is the laminator stamping of their motor what they are using. So this is the design. This one also a permanent magnet synchronous motor. Chevrolet in the year 2016, they started use a permanent magnet synchronous motor with the curved barrier. So this one is a curved barrier. They started to use. These are all the slots for inserting permanent magnets. Okay, so this one is Chevrolet Volt model. Then Honda Freed, they use this model for their electric vehicle. Then Chevrolet Bolt in the year 2017. So you can see in every model the barrier is U-shape or the curved shape. So in some of the applications, they started to use a curved shape. Now the researchers conclude that the curved barriers are the best one for electric vehicle applications. Okay, so we will discuss one by one in the next sessions. This one is the NIDA Corporation's first SRM machine for electric vehicle. Now the EVs started using SRM machine in their application. Okay, especially in high torque. Whenever the machine needs high torque applications, the SRM motors are used, and this one is used for SRM machines are used for lower power applications. Okay, uh, for four-wheeler like cars, the permanent magnet synchronous motors are playing a major role. Okay, but for Tesla, it is induction motor. Okay. In last 10 years, these are all the developments in electric motors. So from 2012, this one is the motor which is used by BMW i3. Then this motor is used by Toyota Prius. We have discussed earlier, right? Then Chevrolet Bolt 2014. This design also we have discussed earlier. This one is the Tesla Model 3 motor. This one is the front and this one is the rear portion. The Chevrolet Bolt and in the year 2017, this is the motor they have used. In 2018 Audi e-tron, this is the front section and this one is the rear section. Okay, this one is the permanent magnet synchronous motor. This one is the Jaguar I-Pace model motor. Okay, the Jaguar also using permanent magnet synchronous machine. Then Nissan Leaf, this is a motor used Nissan Leaf, and this one is used in Tesla Y model. This one is front portion and this one is the rear portion. Okay, so in past 10 years, you can see the developments in electric motors in various industries. Okay, so this may be the future of electric vehicles. Okay, so these are all the types of electric vehicles. I think many sessions have been passed with this type of electric vehicles. Okay, so I will introduce some of the electric vehicles. Okay, so first one, the hybrid electric vehicle. The hybrid electric vehicle have IC engine, also the electric motor. Okay, then the battery for backup, gasoline for the source of IC engines. Then next type, plugged-in hybrid electric vehicles. So this one also have the same features of a hybrid electric vehicle, but in this we can charge the battery of our electric vehicle. Okay, so this is the major change in a plugged-in hybrid electric vehicle. Also, we can uh, 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 charge from the feedback from our electrical motor. Then battery electric vehicle. So the battery electrical vehicle is purely operated by the large batteries. Okay, so here we can charge our battery and we can use our electric vehicle. Okay, so this is the purely on electric. Okay, there is no use of IC engines. For these two types only, they use IC engines. For these two type of electric vehicles, they won't use IC engines. It is purely on electric motors. It is purely operated on electric motors. Okay. The next one, fuel cell electric vehicle. So this one is uses this type of electric vehicle uses fuel cell as well as battery. Okay, the main source of this electric motor is fuel cell. So from fuel cell, the power is supplied to electric motor. Okay, and the hydrogen, and then for fuel cell, we need hydrogen as the input. So this type of electric vehicle needs hydrogen tank to feed the fuel cell. Okay, so from the fuel cell, the output can be used for charging battery as well as powering this electric motor. Okay, so these are all the classifications of electric vehicles: hybrid electric vehicle, plugged-in hybrid electric vehicle, battery electric vehicle, and fuel cell electric vehicle. Okay, so these are all the classifications. Then we can see some of the examples of the manufacturers who are all using this type of machines. Okay, for battery electric vehicles, BEV. So this type of vehicles are used in Tesla Model 3, BMW i3, Nissan Leaf, Tesla X. So these are all the battery electric vehicles. Okay, so the problems in these type of machines, these type of electric vehicles are they need a higher capacity of batteries, and the price will become more, and charging time will be increased. When we are using a higher rating of battery, the charging time will be increased. So this is the another problem, and another problem, need more charging stations. So as our Indian infrastructure, we don't have much charging stations in our country. So we in India, we cannot use purely we cannot depend on battery electrical vehicle. That is why the hybrid electrical vehicles are hybrid electric vehicles and plug-in hybrid electric vehicles are more dominant in India. Okay, then if you talk about features of battery electrical vehicles, the air pollution, air emission is there is no air emissions. then we don't depend on gasoline or something. Okay, and there is no need of oil source. Then a battery range is high and large. When we are using battery operated electric vehicles, uh, this one might have higher range of electric batteries. So they gave in the feature as well as this one may be the problem also. Then commercially available, the batteries are commercially available. So these are all the features of battery operated electric vehicles. Then hybrid electric vehicles, Honda Civic, Toyota Prius, Toyota Camry. So these are all the some of the electric vehicles which are all working under hybrid electric vehicle system. Okay. Then the problem is optimization, because in hybrid electric vehicle, it has to be switched from electric mode to uh, the engine. Okay, IC engine. So the it should be changed from IC engine to battery sorry, electric motor to IC engine to motor. So there is the one problem. And battery engine size may be big because of introducing uh, electric motor in the engine itself. So this is the another problem. And management of energy sources is difficult. Yes, we have two type of energy sources. One is from battery, another one is gasoline. So the management will be very difficult. So the optimization should be uh, optimized more. Okay, then if you speak about features, the emission is very less. Then battery range is long, and the both electric and the fuel can be supplied. Okay, then plugged-in hybrid vehicles. These are all the some of the EVs. RDA3 e-tron, BMW i8, Chevy Volt, Kia Optima, and Ford Fusion. So these are the some of the machines. Electric vehicles uses the topology of plugged-in hybrid electric vehicles. So the problems are same like hybrid electric vehicles. And the next criteria, fuel cell electric vehicles, Toyota Mirai, uh, Hyundai Tucson, Honda Clarity, and Honda Nexo. So these are all the electric vehicles using the same configuration. They started to use fuel cell in their electric vehicles. Okay, these are some of the problems. The hydrogen fuel is the major problem in fuel cell electric vehicles. So these problems are based on fuel. Okay, so fueling facilities are already checked. So it should be the availability is less. Okay, and the cost of the hydrogen is more. Then security also more important. The hydrogen explosion will cause more casualties. Okay, then cost of fuel is high, and safety. So these are the points in problems. Okay, so these are all the electric vehicle types and the examples and problems of the electric vehicles. Okay, we will move on to electric motor design. Okay, so in motor configuration, so these are all the configurations every electric vehicle will contain. Yeah, single motor drive. Okay, so yeah, centralized single motor will be used for a powertrain. Okay, so in this type, a single motor is used for powertrain. So uh, Tesla Polestar 3. So this electric vehicle uses this type of configuration. Then using dual motor, one motor will drive the front end, and another motor will drive back end. Okay, so Tesla Model 3 uses this type of configuration. And triple motor. So in triple motor, two motors are used for driving. This one is rear wheel. Okay, so in wheel type, or this one is the in wheel motors. Then this one is the a separate motor. So this configuration is triple motor. And Audi e-tron S, Tesla Model S, and Tesla Model X. So these are the models uses this type of configuration. And four motor drive. So four wheel drive. So this one is called four wheel drive. So four-wheel drives are under research. If you take Porsche, Tesla, Audi, so these companies are doing research in these four-wheel drives. Okay. When we are using a single motor, the torque and force, the power is very less. When we use multiple numbers of motors, the power will be higher. Okay, when you compare the power between this single motor and multi motors, the multi motor delivers high power than the machine which using a single motor. Okay, so these are the difference between multi-motor drive and single motor drive. Okay, we will move on next topic. Then types of motors in electric vehicles. So in electric vehicles, these are all the major motors they are using. First one is the BLDC motor, brushless DC motor. The brushless DC motor are mainly used in two-wheelers, not in four-wheelers. So in major four-wheelers use the permanent magnet synchronous motor. Okay, then induction motor. So these are all the two motors, the four-wheelers and the heavy electric vehicles are uses. SRM and BLDC motor. These two motors are used in lightweight machine electric vehicles. Okay, so these are the classifications. Um, in next slides, we will discuss what are the challenges in controlling any type of motor. Okay, first we will take a BLDC motor. So in BLDC motor, we have two categories: hub motor and inner rotor motor. The hub motor have outer rotor configuration. So this one is the rotor in this BLDC motor. This one is the stator, uh, and this one have a surface permanent magnet. To drive this outer rotor, they have placed permanent magnet in the surface of stator. Okay, so this one is the shaft, and so this is the configuration of hub motor. So you can see hub motors in most of the two wheelers. Okay, so in two wheelers they use hub motors. Okay, so inner rotor motors are used in geared electric vehicles. Okay, so in geared electric vehicles they use inner rotors. Okay, so this type of motor is used for in-wheel motor drive. So this one is the in-wheel motor drive. This one is the gear motor drive. Okay, so this one is the rotor and this one is the stator. Okay, so in stator they used permanent magnets in the interior portion of stator. So that is why this type of permanent magnets are called interior permanent magnet. Okay, so this one is the rotor, this one is the shaft. Okay, this is the configuration of hub motor and inner rotor BLDC motor. Then we will discuss the problems in BLDC motor. Okay, so when we design a BLDC motor, the main parameter we measure is torque ripple. Okay, so torque ripple is the major problem in every electrical motor design. Okay, when you take BLDC motor, we will discuss torque ripple and other parameters in BLDC. So the common parameter in every electric vehicle is torque ripple. Okay, so we will discuss how the torque ripple can be minimized in every machine. Okay, for BLDC motor, the source of torque ripple is based on the motor control, what control method we are using. So the current commutation and PWM schemes. So this may be the reason for torque ripple and motor structure. So in the structure itself, the torque ripple may produce. Okay, so the current conduction, current commutation, freewheeling diodes. So these may be the reasons of torque ripples and motor nature. So the BLDC motor have a permanent magnet in it. Okay, so the permanent magnet, whenever the motor uses permanent magnet in it, the cocking torque will be produced. Okay, so the cocking torque may be the reason for the torque ripple. The electromagnetic torque, because of the electromagnetic torque produced in BLDC motor, the torque ripple may be produced, and reluctance torque. Because of the reluctance torque, the torque ripple may be produced. Okay, so these are all the motors, type of motors used in electric vehicles: surface mounted motor, salient pole motor. So these are all not effective in electric vehicles. Interior permanent magnet motor are the effective one for electric vehicles. Okay, so these are all the sources of torque ripple in BLDC motor. So we can use many methods. There are many methods in the researchers have produced to overcome this torque ripple problem. Okay, then next mission. Yeah, these are all the techniques the researchers have introduced. Okay, for modified pedaling control. So these are all the methods and adapted techniques. Okay, so the modified pedaling control. In modified pedaling control, the PWM chopping method and low cost digital control techniques are used. And then DC bus voltage control, current control based technique, phase conduction method, model predictive control, direct torque control, FOC control, model adaptive control, soft computing technique. So these are all the some of the methods used for mitigating in the torque ripples in particularly for permanent magnet, BLDC motors. Okay, then permanent magnet synchronous motor. In permanent magnet synchronous motor, these are the major type of motors. First one is the uh, permanent magnet assisted synchronous reluctance motor. So this type of motor have a flex barrier. This one is the flex barrier. So in flex barrier, they insert a permanent magnet in it. Okay, so this one is the rotor. This one is the permanent magnet axial flex machine. This one is the permanent magnet spoke type machine. So in major electric vehicles, they use the spoke type or permanent magnet assisted reluctance motor. Okay. So these are all the limitations in permanent magnet synchronous motors in EVs. Okay, high cost magnetic materials. So the major permanent magnet synchronous motor uses NdFeB, that is neodymium ferran ferran boron. So NdFeB, that is a permanent magnet which is used for PMSM. So we can either use ferrite based materials, okay, the ceramic materials in place of neodymium or SM. Okay, then conventional motor design. So the conventional motor design can be overcome by introducing many other configurations like permanent magnet assisted synchronous reluctance motor, permanent magnet axial flex motor, permanent magnet spoke type motor. So we can use these kind of motors to overcome our conventional motor design. Then torque ripples. So in permanent magnet synchronous motor, the torque ripples can be minimized using these topologies. Motor topology development. So by developing in the development stage itself, we can reduce the torque ripples. Okay, so we will discuss the design things in the next slides. Okay, improving control technique. By improving control technique, also we can reduce the torque ripple. Okay, so this one is the improving torque control technique is based on the after producing a prototype, we can adopt this method. When the motor is in design stage itself, we can control the torque ripples. Okay, so that topic we will discuss in the next slides. Okay, uh, then fault tolerant. We can change the control strategy to limit this drawback. Okay, so these are all the drawbacks and the solution to overcome in permanent magnet synchronous motors, which is used in electric vehicles. Okay, the next one, induction motors. So induction motors have these drawbacks, and these are all the solutions. So in first one, the conductor losses. Okay, so the conductor losses can be minimized by introducing high electric conductivity material. So the material can be changed in induction motor so as to reduce the conductor losses. Okay, then high copper loss. So the high copper loss can be minimized by improving accurate model calculations. Okay, in the design itself, we can uh, reduce the copper losses. Okay, then DTC control techniques. By using DTC control techniques, we can reduce the copper loss. Then less efficiency. We can improve the efficiency of induction motor by introducing um axial length, increasing axial length, and then modifying skew rotor, multi-objective optimization. So the multi-objective optimization can be used in control technique. Okay, so these are all the limitations and solutions of induction motor. So this is the induction motor which is used by Tesla. Okay, then last one, switch reluctance motor. The switch reluctance motor have these two type of machine, radial machine and axial machine. In major electric vehicles, they use radial type of motors. Okay, so this is the axial type of synchronous switch reluctance motor. Then torque density improvement techniques. So these two are the techniques by which we can improve the torque density. Okay, first one is the motor topology development. So in the development stage itself, in the design stage itself, we can improve the torque density. Okay, first one is the increasing number of stator or rotor poles. Okay, this is the one of the method to increase the torque density. Then the next one is the axial flux SRM. When we choose the configuration of SRM, we can choose axial flux type of SRM machine to reduce the improve the torque density. Okay, then optimize design on yoke thickness, axial length, stator pole, rotor pole, or pole arc. So when we design a pole, the pole configurations there are many pole configurations in SRM machines. Okay, so by designing by optimizing the design of uh, these portions, we can improve the torque density. Okay, so by using this method, motor topology, in the design stage itself, we can improve the torque density from 15 newton meter to 45 newton meter. Okay, the next one, high saturation flux density material. By changing the material itself, we can achieve the torque density up to 15 newton meter. Okay, so the first one, improving magnetic loading of machine or material. So the magnetic loading can be improved in the design stage itself. Okay, so this will improve the torque. Okay, then cobalt ferrite material or high cost, increasing high loss. So increasing core loss. So this may influence the improving torque density. Okay, so these are all the methods by which we can improve torque density. Okay, we will discuss these topics one by one. Then acoustic noise reduction. So in acoustic noise reduction, these are all the methods, stator and rotor topology changes. So in the design stage itself, the vibrations and acoustic noise can be controlled by optimally designing stator and rotor. Okay, so in stator and rotor topology design, the first method is stator spacer slot wedge. Then the second one, two stator or rotor sandwich. The sandwich rotor design can be introduced, and the cylindrical rotor. The cylindrical rotor may cancel the acoustic noises. There are some other configurations also there. We will discuss. Then stator rotor pole skewed. So the skewed poles also can be used to mitigate these acoustic noises. Then control techniques. So in control techniques, independent stator pole current control, current profiling, direct instantaneous force control, hybrid excitation, two-stage commutation. So these are all the methods the researchers are using to control the acoustic noise. Okay. Then torque ripple mitigation technique. So in SRM also, this is the major problem, torque ripple. So the torque ripple can be reduced by using these two methods, by optimally design the topology and advanced control techniques. So we have some other advanced control techniques in SRM machine. These are all the advanced control techniques. First one is torque control and another one is current control. In torque control, we have two methods. One is indirect torque control and direct torque control. In indirect torque control, there are methods, and in direct torque control, there are methods used. In current control, intelligent control, model-based control, hysteresis control. So these are all the controls they use for SRM machines. Okay. Then the major problem can be reduced by using optimal design of any topology. Okay. So by using this method, the majority of the problem will be reduced. Okay. So if you take any electrical machine, so these are all the steps the machine has to be followed. Okay. So the first one, design data. Any machine should be designed based on the availability of material, cost effectiveness. So there are some of the parameters that first we consider, and the motor parameters are designed. So this is the design stage, and in evaluation stage, these are all the stages. First one, choosing the best configuration. So if you take BLDC motor, there are two configurations. One is a hub type of motor and outer rotor configuration. So in outer rotor, inner rotor configuration. So in inner rotor configuration also, there are many type of configurations, like position of permanent magnet, that and all. In permanent magnet synchronous machine also, we have many configurations. Okay. So in every, if you take any machine, there are many configurations. So apart from those configurations, we need to choose any one configuration based on the our requirement. Okay. So if our objective is to reduce the torque ripple, then we need to choose the configuration which produces less torque ripple and less losses. Okay. Then selection of best material. Next stage is selection of best material. Okay. So the in material wise, in design, the materials can be decided for producing less losses. Okay. For loss minimization, this stage can be used. Then vibration analysis. After designing these, after analyzing electromagnetic analysis, okay, the dark ripple minimization, loss minimization. So after these stages, we need to analyze the machine for the vibration. Okay, how much the vibration can be produced. The researchers in their research articles, they have mentioned that if the torque ripples are minimized, the vibration also can be minimized. Okay. So we will discuss how the configurations are more important to minimize the vibration. Okay. So we will discuss in some other slides. Okay. In thermal analysis are also more important in designing a machine. Okay. This can be done by computational fluid dynamics, CFD. Okay. So I, then through these stages, we can construct energy efficient machine. Okay. So in further slides, I will consider the switch reluctance motor for the analysis. Okay. FEA. So why we use FEA? So these stages need a finite element analysis. Okay, so the why we need finite element analysis is in traditional method. They first they used to design a machine, then they will prototype, then they will test the machine, then they will give it to a production section. Okay, so in production also they will face some other problems. In testing also they will face some problems. In prototyping also they will face some of the problems. Okay, after this only they redesign, and they will again prototype and retesting and reproducing. So these steps will be repeated again. So the cost of the materials will be wasted. Okay, so when we started using finite element analysis for designing any uh, equipment or any material, the cost of prototyping is minimized. Okay, so in the CAD design itself, we can we can conclude the best type of machine. Okay, so that is why the finite element analysis is more important in designing electric motors or electric vehicles. Okay, so these are all the stages of finite element analysis. First one, geometry. First, we create a geometry of any electric vehicle using nodal points. Okay. Then next one is the pre-process. Pre-process is consist of uh, designing a mesh and defining the initial conditions that are. So these are all the pre-process. Then solve. So after that we solve the problem for electromagnetic analysis or vibration analysis or thermal analysis. So for every analysis, the FEA software will do this. Then post processing. In post processing we visualize the results. Okay, so these are all the stages. In FEA, these are all the softwares we can use for designing electric motors. Okay, first one is magnet. Magnet is the software which is used for mainly for electromagnetic analysis only. Okay, this needs additional software for 2D design. Okay, we can do 2D design in magnet software itself, but it is very difficult and conventional method for 2D design. So we can use any other 2D design software or 3D design software. So from that we can import the design and we can do electromagnetic analysis using magnet software. Then GMAC. So this software can be used for permanent magnet synchronous machines, BLDC motor, switch reluctance motor. They have they gave some of the pre-designed models, so we can modify those models and we can use. Okay, so this is the best tool. And the motor solve. So this software has BLDC motor. So in every software they have these prototypes. Okay, so but these softwares have templates for every machine. Okay, but in other cases EM works also having some templates for every machine. So in ANSYS they don't give the prototype, but we can import from these softwares. In magnet we can export the data to ANSYS, that is um, IGS file. Then we can import it to ANSYS for thermal analysis and vibration analysis. Okay, so in EM works you can do all these works for electromagnetic analysis, vibration analysis, and thermal analysis. You can use this software and Max. Okay, so these are all the softwares can be used for all the analysis. So you can do all the analysis for using these softwares. Okay, so these are all the some softwares for FEA analysis for our electric motors. Okay, then in further slides I will discuss about the stages of motor design. Okay, so these stages will be discussed from this slide. Okay, so first one, configuration selection. Okay, so in configuration selection, here I have mentioned three configurations: mutually coupled SRM, long flux SRM, and short flux SRM. Okay, so these configurations are based on how the flux is traveled. Okay, so the long flux SRM have the longest flux path. Okay, so from this machine, I am reducing the flux lines. Okay, so the flux lines are traveled all over the material, so the losses may be increased. Okay, so if you reduce the flux lines or flux path, the losses may be reduced. Okay, so that is why these configurations are used. So these are all the design parameters. By using traditional equations, we can derive these values. Okay, these are all the uh, models. Okay, so you can see long flux XRM and short mutually coupled SRM are having same model, same 3D model, but the winding connection is differs. Okay, in short flux SRM, you can see here I have increased the number of stator poles and number of rotor poles. The stator poles are same. Uh, Increase the rotor poles. Okay. Okay, sorry, this one is the outer rotor. I have increased the number of stator poles. Okay, then only we can reduce the flux path. Okay, so these are all the difference between long flux XRM and mutually coupled SRM. The only difference is the winding connection, and this one is the shortest flux path SRM. SF SRM, and this one have the more number of stator poles. Okay, so here these four are connected to a single yeah, phase A. Okay, A1, A2, A3, and A4 are connected with the phase A. And B1, B2, B3, and B4, these are all connected to base phase B, and this is for phase C. Okay, so this is how the connection is made. So this one explains the flex path. Okay, so this one have longest flex path. Okay, so the flex will travel a long way. Okay, so this one have a short flex path, a mutually coupled machine. Okay, so this area will be reduced. Okay, so here you can see the flex path is very much reduced. So this one have shortest flex path. Okay, so by this method we can reduce the uh, torque ripple and losses. Okay, so the flux path is reduced, uh, the losses will be reduced. Okay, these are the flux lines. This is the torque characteristics. So this is the formula for torque ripple: maximum torque minus minimum torque divided by average torque. Okay, so we can calculate using these parameters. So this is the minimum torque. This one is phase A, this one is phase B, and this one is phase C. So this is the meeting point of phase C and phase A. So this is the minimum torque of this machine, and this one is the maximum torque of this machine. Okay, and this is the average. So average can be taken by taking average of these points. Okay, so this is the average torque. Okay, so this is the analysis of these three configurations: long flux XRM, mutually coupled SRM, and short flux SRM. Okay, so in this analysis, the torque ripple parameter is considered. Okay, so here you can see long flux SRM have 0.9097 and mutually coupled have 1.2181. Short flux SRM have 0.8002. So you can see the torque ripple have been minimized in short flux SRM. In losses, so you can see uh, the losses are minimized here. So ohmic losses, here it is 35.8, here it is 22.3, and here it is 20.48. The total loss, you can see the total loss is very much less in short flex SRM, because the flex path is very much reduced in this case. Okay, so if you calculate the efficiency, it is more in this case, okay, compared to long flex XRM. Okay, this is the efficiency calculation. Efficiency equal to output power divided by input power. We know that the output power is input power minus power loss divided by input power. So here we have used a 250 watts machine. So 250 is the input power minus the losses. So here the losses are 39.15. 39.15 divided by 250. So this gives efficiency of 84.34 percentage. So this is the efficiency of this machine. Okay, so this is the basic uh, parameter of SFS SRM machine. Okay, then we need to consider material selection. Okay, so in material selection there are many materials available. So for core material there are non-oriented silicon steels. So these are all the conventional electric materials which are all used in our day-to-day induction motor, transformers. Okay, so they use these type of non-oriented silicon steels. In market nowadays, these materials are available. Advanced materials, amorphous alloys, super cores, cobalt iron alloys. Okay, see the Wacoflex 50, Hyperco 50A. So these are all the major materials nowadays the industries are started using. And these materials, Fe based and cobalt based. So Fe based and CO based. So these materials are called met glass and vitrovac. Okay, so then vacuum sized materials also started used in research. Okay, then other materials, dual phase material, nanocrystalline alloys, soft compute magnetic composites. So these are the some other materials, advanced materials used for core materials. Okay. From this, I have selected some of the materials, and I have analyzed the BH curve. So in the BH curve itself, you can see these three materials. This one is Hyperco 50A, and this one is Wacoflex 50. This one is Wacoder 50. So these three materials performed well because in the magnetic field intensity, for the minimal magnetic field intensity, they have achieved yeah, maximum magnetic flux density. Okay, so this may perform well in any motor. Okay, Wacoflex 50, Wacoder 50, and Hypergo 50. Okay, not only this one, we need to consider loss curve also. So in the loss curve also, you can see the last one, Wacoflex 50. So this one have yeah, very much less uh, loss characteristics. Okay, then next one, this one is the Hyperco 50. So these two materials are repeating, Hyperco 15 and Wacoflex 50. The next material, this one, M-19, this material. So this material used very much used in our transformer design, induction motor design. So this is the material. Then other two materials we can consider Wacoflex 50 and Hyperco 50A in our analysis. Okay. Then flux linkage curve. So this curve explains the how the flux linkage having happened between stator and rotor. Okay, so for every angle the flux linkage have been analyzed. These three materials performed well. Okay, this one have a very much higher flux linkage. This material is Hyperco 50. This material is Wacoflex 50, and this material is Wacoder 50. Same three materials which are performed well in BH curve have performed well in our machine. So in our machine also, these three materials performed well. Okay, then if you take other two analysis, so in this analysis the torque have been analyzed. Okay, so in this table also you can see these three materials have produced minimal torque ripple. Okay, so here in the base material M19 have minimum torque, but if you see the torque average, it is less. But in other materials, the average torques are more. That is why I have highlighted these three materials. Okay, so other materials are having more torque ripple and less average torque. Okay, so here Walker-Flux 50 performed well and gives maximum average torque of 2.655 and minimal torque ripple of 0.8138. Okay, then we will consider the loss characteristics. So in loss characteristics, you can see Hyperco 50. So in the characteristics itself, it shows these three materials: Walker-Flux 50, Hyperco 50, and walk out of 50. These materials will perform well. So same here you can see these three materials gave minimal losses. Here walk out flux 50, walk out of 50, 41, then hyperco 50, 29. So these materials performed well. Among these, Walker-Flux 50 performed well. Okay, so you can take a machine configuration with Walker-Flux 50 material for the further analysis. Okay, so here I am taking a Walker-Flux 50 material with the best performed configuration, which is short flux SRM with Walker-Flux 50 material for the further analysis. So next analysis, pole configuration. Okay, when you are considering pole configuration, there are many pole configurations available. For this analysis, I have taken a claw pole, asymmetric pole, traditional pole, and adding pole shoe and tapered pole. Okay, so these are all the configurations. So the claw pole, the base in claw pole, base have minimal length and head have the maximum length. Okay, the tapered pole is reverse. So in base, the length is higher, and in pole face the length is low. Okay, this one is asymmetric arrangement. This one is a traditional pole, have a parallel pole. This one is introducing pole shoe in pole. Okay, so these are all the analysis in claw pole rotor. These are all the minimum torque, maximum torque, average torque, and torque ripple. This one is the asymmetric rotor pole. In asymmetric rotor pole also, the width of asymmetric arrangement is increased, so 2 millimeter and 3 millimeter. This one is the traditional pole. This one is the introducing pole shoe in poles. This one is a tapered pole. In tapered pole also, the angle of tapering is increased. Okay. So in the analysis, you can see this kind of pole configuration performed well, which gives the torque ripple of 0.6865. Okay, this is how you should select the pole configuration. Okay, by choosing pole configuration, you should consider a torque characteristics as well as loss characteristics. Okay, so these are all the some of the pole configurations I have listed here for the understanding purpose. There are some other configurations which can be used for minimizing torque ripple as well as noises. Okay, here I have analyzed some of the configuration and their torque ripple minimization percentage. Okay, so this one is the slanting rotor teeth. So this one can reduce torque ripple by 2%. Okay, so this one is slant is 0.5 millimeter, so this length is 0.5 millimeter. This type of rotor is called serrated rotor teeth. Okay, this one they have introduced some rotor teeth. Okay, this one will reduce the torque ripple and increase the average torque. Okay, then skewed rotor, skewing of rotor may reduce the torque ripple. So this one reduces the torque ripple by 3%. And finned rotor teeth, the rotor teeth are finned in the either sides. So this one will reduce the torque ripple by 15%, and the average torque improved by 12.5%. This one is the introducing notch in rotor poles. Introducing notch in a pole tip or at the base, you can introduce in any places. Okay, here they have introduced notch in pole tip. Okay, so this one will reduce the torque ripple by 4.4 percentage. This one is the projecting notch. So this one is the projecting notch. Okay, so this one will reduce the torque ripple by 34%. Okay, so this one performed well. uh, then this one is the grills, introducing grills in rotor teeth. This one reduces the torque ripple by 2.6 percentage. And these are some other configurations. Variation in stator and rotor pole arc. Okay, so this is the pole arc variations. This is the stator one, and this is the rotor one. Okay, so you can vary the pole arc width to reduce the torque ripple. So this one also produces less torque ripple than other configurations. Then ununiform air gap. Okay, by giving ununiform air gap between stator and rotor also reduces the torque. Then increasing number of rotor poles. Um, the increasing the number of rotor poles also reducing the torque ripple. Then tailing pole tip and a curved teeth rotor. So this is the tailing pole tip, and this one is the curved teeth. So this one also reduces torque ripple. This one reduces torque ripple by 1.25 percentage. These are all the optimized rotors. And this one is the introducing flex bridges. Okay, uh, like in a permanent magnet synchronous motors, in SRM machine also there are researchers introducing flex barriers. Okay, so here this one is the flex bridges. These are the gaps between the rotors. Okay, so this one reduces the torque ripple by 23%. And this method adding layers in a rotor. Okay, so this one reduces the torque ripple by 28%, and this one is the asymmetric arrangement of stator and rotor pole. This one reduces the torque ripple by 38.8%. Okay, so among these methods, adding flex bridges, adding layers, then asymmetric arrangement, uh, this one projecting a notch. So these methods performed well in reducing the torque ripple. Okay, so you can try these methods in your research also. So these methods gave very much torque ripple reduction. Okay, then adding permanent magnets in stator poles. So next method. Uh, so here I gave some of the material, ceramic material, samarium cobalt, neodymium iron boron. So these are all the materials I have taken, and the combination of these materials, combination of Ce and samarium cobalt and neodymium iron boron, neodymium iron boron and ceramic. So these are all the considerations. So here, these are all the places where the permanent magnets are introduced in the stators. Okay. So this is the torque characteristics after introducing permanent magnet. Uh, so all these methods are performed the same. Okay, the torque ripples are the torque characteristics are same. When we consider excuse me. So when we consider a permanent magnet in any machine, you should consider cogging torque. Okay, so these are all the cogging torque of machine with various permanent magnets. Okay, among this red color one, this one have very minimal cogging torque. Okay, so this is the combination of ceramic and samarium cobalt material. Okay, so this one performed well because this one gave a very low cogging torque. But if you take other materials, uh, uh, all other materials are producing very much higher cogging torques. Okay, Then other material, samarium cobalt. So samarium cobalt also producing less cogging torque. Okay. So this is the comparison between all other materials with uh, the tapered pole. This design is the best design we have considered in the last session. Sorry, last pole configuration. Okay, so here uh, you can see the torque ripple produced by using ceramic and samarium cobalt is very much less. So you can introduce a permanent magnet in stator also. For some other configurations, the permanent magnet introduction may reduce the torque ripple, but it is not it, it's not in all the cases. Okay, so in some other cases, the introduction of permanent magnet may increase the torque ripple. Okay, so whenever the design needs permanent magnet in it, so you can introduce. Okay, so by introducing this permanent magnet in this machine may increase the cost of machine. Okay, the ceramic and samarium cobalt is very much uh, higher cost. Okay, so it may increase the cost of machine. So the 0.685 and 0.607 is not a very big. It's not giving very a big difference. Okay, then loss wise, so you can see both are having nearly same 26.01 to 26.22. So both are giving very near losses. Okay, so this is the option. Okay, this is the option for reducing torque ripple. The next one, vibration analysis. So the vibration analysis are used to identify in which frequency the machine should not be operated. Okay, so in design wise, the vibrations can be reduced by reducing torque ripple. Okay, so this method can be used to predict the vibration amplitude of SRM so that we will not operate that machine in that frequency. Okay, in vibration analysis, the first step is model analysis. In model analysis, we used to take uh, analysis for the four to five modes. Okay, here the machine have taken five modes. In every mode, in mode one, this is the frequency and this is the displacement. In mode five, this is the frequency and this is the displacement. Okay, so you can see in mode four, the displacement is more. Okay, 1.3131. So this is the maximum displacement have been taken in analysis. Okay, so these are all the harmonic analysis. One is for radial direction and another one is for tangential direction. In both at the frequency of 400 hertz, sorry, 4000 hertz, the displacement is more. Okay, and another frequency 2400, 2400 and 4100. For these two frequencies, we are getting amplitudes. Okay, 2400 and 4100. So the machine should not be operated in these two frequencies. Okay. So these are all the stages. So first we have designed a machine with a design data, and we have chosen a best configuration. Then we have chosen best material. Then we have introduced permanent magnet. Then vibration analysis. I have not included thermal analysis in this slide. Um, if time permits, we will discuss in the future sessions. Okay. These are all the references. In this slide, you can see many of the images are taken from the first paper and second paper. And the third reference is my article. Uh, the last portion, which covers these switch reluctance motors, are from this article. Okay. Any queries?
Participants,
Okay.
Participants, if you have any queries, you can ask. Arun sir,
Now
there
we
are
can
some questions which have been
turn
asked
on.
in message.
Now we can turn on your mic and we can speak.
Good evening, sir. This is Shinoy here. Am I audible, sir?
Yes, sir. Yeah, yeah, you are audible, sir.
Sir, actually, in the slides you have shown that the rotor itself, there will be some slotting, shaping, and all in order to
Yes,
reduce the torque. I mean,
yes.
in order to reduce the torque ripple.
Dark ripple.
Yes, but effectively, the air gap length increases and it will overall torque also will get reduced, right, sir?
Yes, sir. Wait a minute, sir. So in this slide, you are asking, right?
No, sir. You have shown as a slotted kind of thing. Maybe the starting itself, different slotted shapes where there will be in the rotor there will be gaps. In the stator also you have shown it. Yes, sir. Here you can see that as flux barriers you have shown, sir.
Yes.
Effectively, the uh, air gap length also get increased, right, sir? Because of this slotting.
No, you can see in the application also they have introduced a flex barrier. Okay, here in Toyota Prius, so every machine you can see they have introduced flex barrier. These are the flex barriers. So it will not affect the your torque. Any other questions, sir? That is why we are adding permanent magnet, sir. Any other
Sir,
questions?
one question is posted in the chat box, sir. Sarojini, uh, sir, is SRM motor is still under research or it is incorporated in any EV car recently?
Uh, Actually, SRM machines are used in hub type motors. They started to using. You can see this NIDA corporation started to produce SRM machines for electric vehicles. Okay, it has been started to they started to use in Nissan. I think exactly. I don't know the model. In Nissan, they started to use SRM machines. Any other questions, sir?
Yes, sir. One more question. How to check design the same person, the Sarojini Hari question. How to check designed parameters of any motors is within limit?
There are standards which is available like IEEE standards. There are some standards, so you can check it with those standards.
Prabhu Sundarmurthy has posted a question. Sir, if magnet included in stator, what will happen to thermal?
Actually, introducing magnet in stator.
If the magnet included in stator, what is the German?
Okay, I think he's asking in my slide. So in this one, so here we have covered the stator. So the computational fluid dynamics will the flow of air will affect. That is why I have mentioned that if the machine needs permanent magnet in stator, we can introduce. Okay, so for this design, the thermal the increase in temperature will be there.
So one more question from the Prabhu Sunamurthy sir. In such case, reluctance torque will be added to reduce torque ripple. So Prabhu sir, can you unmute and can raise your question back to sir?
Prabhu sir, can you tell me
Sir,
in which slide you are
yes.
in?
Sir, just now you are posting one slide now, sir. You have shown one slide, ring
This
phase,
one?
that one only, sir.
Yes, sir.
So whether the reluctant torques will be added to the permanent magnet torque or some Coggin torque impact will be there.
Some cogging torque impact will be there, sir.
Okay, okay. Okay, thank you, sir. Thank you, sir.
Thank you.
Nirmala Dharmalingam, can you unmute yourself and can post your question? Thirukumaran sir, Vivek sir,
Yes, sir.
sir you can post your question now, sir.
Shall I ask, sir?
Yes,
Yes,
sir,
sir.
you can ask.
Sir, I had some doubt regarding the, for example, if a permanent magnet synchronous motor, we are saying exactly as AC, how we are defining, sir, how we are exactly defining it's a AC motor, and, based upon the construction or else some other thing, sir.
Sir, it is based on the conversion in windings, sir. Okay, in permanent magnet machines. So this is the configuration. Okay, this one will be work based on the conversion of AC voltage in these windings.
Okay, sir.
Thirukumaran sir, can you raise your questions, sir?
So one more doubt is there, sir. Can I ask?
Yes, sir. Yes, sir.
Actually, the thing is, sir, in the stator, we can put the flux barriers, but in one of the slide you are shown in the rotor also flux barriers were put. So, as such, lamination when we are wire cutting it, is it feasible to do so?
In permanent magnet synchronous motor, they won't introduce barrier in stator, sir. They will introduce only in rotor, not in the stator.
Okay, sir. In SRM, sir.
In our SRM, we can introduce flux barrier in both rotor and stator, sir, because we have space for introducing flex barrier. So you can introduce flex barrier here also. In stator also you can introduce flex barrier.
Okay, sir. In the permanent magnet synchronous motor, as you shown in Toyota vehicle and also,
Yes.
is there any particular significance of putting that particular shape because it is been followed in other in the other second configuration also similar pattern is been followed.
Sorry, in 2004, this is the model, sir. They have introduced flex barrier and they have inserted permanent magnet to compensate the torque. After that, they have produced many configurations like this one and this one.
So you mean to say that since we are putting a barrier in the stator, additionally the magnet thickness of the permanent magnet needs to be increased?
Yes, sir. Here you can see, here the flux barrier is more, the width of permanent magnet is more here.
Okay, okay, okay. Thank you, sir.
Yeah.
Any other questions from participants can raise. You can unmute yourself and you can speak. Vivek, sir? I think, Vinod, sir? Shall we conclude, sir?
If there is no more questions,
Okay, sir.
if there is no more question, then we can wind up, sir.
Okay, sir. Today's session video will be uploaded tomorrow in YouTube. The same will be posted in the WhatsApp group also by tomorrow. And regarding certificate, we will post the certificate, all the certificate in the WhatsApp group as possible. We will post in the email too. You can download. You can search your name and you can take your certificate. I hope I am clear. Thank you. So, thank you so much, Saravanan sir, for the nice presentation from the beginning about the SRM motor design and the challenges in the SRM motor. So, right from the industry point of view, design point of view, everything, sir. Thank you so much for your nice presentation. Thank you, sir. I welcome Vinod sir to give the vote of thanks.
Yeah, very good evening to all. Sir, let us take a group photo. So I think I request all you to kindly, if possible, kindly to switch on your camera. Arul sir?
Yes, sir.
Yeah, one.
I will switch on and yes, sir. Now it's.
Yeah, participants, if you kindly switch on your camera, then we can have one shot and then we can go for vote of thanks.
Sir, we can't able to turn on our camera. Host
No,
had deactivated.
sir, I think the camera have to be turned on by the host.
Okay, 1 second, sir.
Sir, now it is okay, sir.
Yeah, thank you, sir. Arul sir, just take a screenshot, sir.
Sure, sir.
Is it okay, sir?
Sir, I need to take another. 1 second. Please hold a minute.
You think it is automatically
Okay.
moving to the next screen, sir? Okay, thank you, participants. Thank you for turning on your video.
Thank you so much, sir. Thank you so much.
Yeah, let us go for vote of thanks. So
Thank you, sir.
on behalf of Department of Electrical and Electronics Engineering, Jerusalem College, first of all, I like to thank the management for giving this opportunity. Then I like to thank the principal sir. Then I like to thank our Dean Student Affairs, Dr. V. Jamuna ma'am, for continued support in organizing such events. I like to thank all the faculty members of the department. And finally, without participants, we cannot make an event successful. So I like to thank all the participants for showing their interest. On all the 6 days, the total number of participants were more than 120 to 130. So thank you all. And if there is any such events or any program, we will communicate to the WhatsApp group. And regarding the certificate, for all registered candidates, certificates will be provided through WhatsApp. Thank you all. Once again, I like to thank all the participants. Thank you.
Thank you all the participants. Thank you so much for the participation.
Okay, sir. Even I think you can post the feedback link.
Yes, sir.
Thank you, sir.
Thank you.
Participant can
Sir, send me the certificate through email, sir.
possibly it will be
But
emailed there,
by
but
today night itself, now within half an hour to 1 hour, we will send it in that WhatsApp group itself, sir.
Okay, sir. You send it through email also, sir.
sure.
Yeah, okay, sir.
Thank you, sir.
we will provide the link. We will upload the certificates in the drive and we will provide the link through emails.
Okay, sir.
Okay.
Feedback link is being posted now, sir. Arul, sir.